All right, we're going to jump right in and demystify AI by focusing on one single powerful idea. This comes from one of the most important books in the entire field, and it's the key concept that links everything from a world champion chess computer all the way to a self-driving car.
So, let me start by asking you a question. What could a chess-playing AI, a self-driving car, and one of those little robot vacuum cleaners possibly have in common? I mean, on the surface, they seem like they're from totally different universes, right? But they are all built on the exact same fundamental principle.
And the answer is, they are all what the field of AI calls intelligent agents. Now, this isn't just some jargon. This is the central unifying idea of all modern artificial intelligence. Seriously, if you can really get your head around this one concept, everything else about AI just starts to click into place.
So what in the world is an intelligent agent? Well, let's break it down. The concept is actually way simpler than it sounds, but it's also incredibly powerful.
At its absolute core, an agent is just anything that can sense its environment and then act on it. You know, you are an agent. Your eyes, your ears, your sense of touch, those are your sensors. And your hands, your legs, your voice, those are your actuators. You take in information, you process it, and you do something. Well, a robot, it's the same deal. It just uses things like cameras and microphones for sensors and motors and wheels for actuators.
In this simple loop, perceive, think, act is the heartbeat of every single intelligent agent. It's just this constant, never-ending cycle of sensing the world, figuring out what it means based on its programming, and then deciding what to do next.
But, this whole agent-focused idea seems pretty neat and tidy now, but it wasn't always so clear. For a long, long time, the pioneers of AI were actually deeply divided over a really basic question. What are we even trying to do here? What's the end goal? You can kind of break down the whole debate into these four camps. Should we build machines that think just like us humans, with all our weird biases and quirks? Or is it enough if they just act human? On the other hand, should we even be comparing them to us at all? Maybe the goal should be a perfect, ideal kind of rationality, logic on a whole other level. These questions really pulled the field in a bunch of different directions for years. So where do we finally land? Well, the modern approach has pretty much planted its flag in one of these boxes. Building agents that act rationally. The goal isn't to perfectly copy a human brain. The goal is to build systems that consistently make the best possible moves to achieve their objectives. This just gives us a much more practical and, frankly, a more scientific way to build and test AIs. But man, the road to get here was a total roller coaster. Seriously, the history of AI is not this nice, clean line of steady progress. It's this wild story of incredible highs and devastating lows, of massive optimism followed by these periods of crushing disappointment, and all of it taught the field some very, very hard lessons.
It all kicked off in 1956, and that sparked this era of just crazy optimism. The first successes were so amazing that any little program that could solve a simple puzzle felt like magic. But then, wham, the 1970s hit, and reality set in. Researchers slammed headfirst into the unbelievable complexity of real-world problems. The 80s saw a bit of a comeback with so-called expert systems, but then another crash. It really wasn't until the late 80s that the field got back on its feet with the more rigorous, scientific approach that we still use today.
And to really get a feel for that early hype, you have to hear this quote from Herbert Simon, one of the founding fathers of AI. Back in 1957, he said that machines that could think, learn, and create were already here and would soon solve any problem a human could. I mean, wow, the confidence was just off the charts.
But you know what happens with that kind of hype, right? It leads to promises that just can't be delivered. See, the early AIs were great at little toy problems, but they completely fell apart in the real world. Why? Because as problems get even a little more complex, the number of possible choices just explodes. It's a nightmare called the combinatorial explosion. And when those promised breakthroughs never showed up, the funding vanished, and the field plunged into a long, cold period we now call the AI winter.
Okay, so after clawing their way out of that AI winter, having learned some really tough lessons, how do we actually go about building these rational agents today? What's the blueprint?
The modern definition of rational is super precise. It means that based on everything it's ever seen, the agent will always choose the action that it expects will maximize its score. Think of it like a video game character that's programmed to always make the move that gets the most points. It's not about being logical in some abstract sense, it's about getting the best possible outcome. So, before an engineer ever writes a single line of code, they always start with something called the PEAS framework. It's a simple little acronym that forces you to get crystal clear about the problem by asking 4 questions. What's the performance measure? What's the environment? What are the actuators? And what are the sensors?
Let's make this concrete. Imagine a medical diagnosis AI. The performance measure, it's not just get the diagnosis right. No way. It's also about making sure the patient stays healthy, keeping costs down, and oh yeah, not getting sued. The environment includes the patient, the hospital, the staff. Its actuators are how it acts on the world, so the questions and tests it puts on a screen. And its sensors, the keyboard where a human types in symptoms. See? Laying it all out like this is the critical first step.
Okay, so once you've got your P's in a row, you can start designing the agent's actual program, its brain. And these programs come in a whole range of flavors, from incredibly simple to mind-bogglingly complex.
The most basic type is a simple reflex agent. You can think of its motto as, I see it, I do it. It runs on pure if-then rules. You know, if the car ahead brakes, then I brake. It only cares about what's happening right this second. It has no memory, no planning, just pure knee-jerk reaction. Now let's level up to the model-based agent. This agent is smarter because it keeps an internal model, like a little map of how the world works, in its head. This lets it handle situations where it can't see everything. A self-driving car needs this, right? It has to remember that the cyclist it just saw is probably still there, even if they've gone behind a truck for a second.
But what if we want an agent to be more than just reactive? Well, we give it a goal. A goal-based agent knows where it's trying to go, so now its actions aren't just based on what's happening now. It considers what will get it closer to its destination. This makes its behavior way more flexible and, frankly, a lot more intelligent.
All right, now we're at the top tier, the utility-based agent. See, a goal is kind of a black and white thing. You either reach it or you don't. But utility, that's about shades of gray. It gives the agent a way to measure how happy or satisfied it would be with different outcomes. This is huge because it lets the agent make trade-offs between conflicting goals, like speed versus safety. It's not just about getting to the destination. It's about finding the best trip possible.
Okay, so we've taken a quick tour through the foundations of AI, from its wild history to the blueprints for an agent's brain. So what's the big idea here? What's the one thing you should absolutely take away from all this?
It's this, right here. The idea of the rational agent is the master key that unlocks all of modern AI. It doesn't matter if we're talking about an AI that understands language, or sees the world, or controls a robot. The ultimate goal is always to build components for agents that can perceive, reason, and act effectively. It all comes back to the agent. And that leaves us with one final and kind of profound thought. We're getting really, really good at building these rational agents that maximize their performance measures. But we have to ask ourselves, what happens when the performance measures we give them, their definition of a good outcome, doesn't perfectly align with our own? That's the question that takes this whole topic out of the textbook and into the real world.